What do the shape of electron orbitals in the hydrogen atom, variations in the gravitational field of the Earth, and the temperature fluctuations of the early universe all have in common? At first glance, not much. These are widely different systems playing out on vastly different scales, from the subatomic to the cosmic. And yet, there's a deep mathematical thread connecting them. In this video, we'll explore how to describe all these intricate wiggly patterns, not just visually, but mathematically. And in doing so, we'll uncover the hidden structures beneath them. Structures that offer insight into both the tiniest building blocks of matter and the large-scale composition and geometry of the universe itself. But before diving into equations, let's take a moment to understand what we're actually dealing with. What could a common description of our three examples here look like? If we look at the two examples on the right, they basically look like functions defined on a sphere. And since the size of the sphere is arbitrary, we basically have a function f that assigns a value to each direction. The direction of a point from the origin can be described by the polar angle theta, which can range from 0 to pi, or in other words from the north to the south pole, and the azimuthal angle phi, which can range from 0 to 2 pi, where 2 pi corresponds to a full rotation around the z-axis. Our function f therefore assigns a value to each possible pair of theta and phi, and this value can for example be a real or a complex number. One way to visualize such a function is with a color map or a heat map on the surface of a sphere. Red regions might represent higher values, and blue regions lower values or negative ones. This is analogous to our visualization of the temperature fluctuations of the early universe in each direction. Another approach is to show elevation on a sphere, where we deform the sphere outward or inward depending on the function's value, like a 3D topographic map. This corresponds to our visualizations of the variations in the Earth's gravitational field. Now, as I already said, the actual radius of the sphere is somewhat arbitrary, as our function only depends on the angular coordinates theta and phi. We can therefore also use the total distance to the origin to indicate the function value at a given direction. Since there are only positive distances from the origin, we either have to show the magnitude of the function values, or we color code the parts where our function values are positive or negative, like in our example here. This visualization is often chosen to illustrate the directional dependence in atomic orbitals. If we have a complex valued function, like it is mostly the case in quantum mechanics, we either have to plot the real and imaginary parts separately, or we only visualize the magnitude of the complex values. We will mostly focus on complex valued functions in this video, as it is more general and it also contains the case of the real valued functions. Alright, now that we've seen what we're dealing with and how we can visualize these things, let's examine these functions in more detail. Since our functions basically live on a sphere, there's a natural constraint that they must obey. When rotating all the way around the sphere, the function's values should repeat, so there's a built-in periodicity. In order to enforce that periodicity, we require that the function be periodic in phi, repeating exactly after each full turn of 2 pi. Satisfying this requirement is enough to ensure periodicity in any direction. Now, do we already know about any methods to tackle complicated periodic functions mathematically? Well, if you've studied Fourier series before, you already know one powerful trick. You can take a complicated periodic 1D function and break it down into an infinite series of sines and cosines of different frequencies. These sines and cosines are therefore the basic building blocks or basis functions of general periodic functions of one variable. So, since we are in 1D and our function is periodic, we already know how to deal with functions defined on a circle. But what if the domain isn't one-dimensional but the entire 2D surface of a sphere? To answer that, let's briefly review the essential ideas behind the Fourier series, just enough to see how the story extends from the circle to the sphere. I will assume that you are already somewhat familiar with the Fourier series, but if not, I will link to some helpful videos explaining the core concepts in more detail. As we have seen, a real-valued function with a period p can be described as a linear combination of sines and cosines of different frequencies, and an additional constant shift. This is the Fourier series for real-valued p-periodic functions. Each term captures a different frequency component, like musical notes blending into a chord. But there's a more elegant version when we look at complex numbers. Instead of using separate sine and cosine terms, we can unify everything using complex exponentials, where the sum over k now goes over all integer values. So in the 1D case, our basic building blocks are complex exponentials oscillating at integer multiples of the base frequency. This base frequency is exactly one oscillation on the period p. We denote these basis functions by ek, where k denotes the integer multiple of the base frequency. Now, just as vectors in R2 can be expressed as linear combinations of two basis vectors ek, periodic functions can be thought of as infinite-dimensional vectors that can be expressed as linear combinations of our infinite number of basis functions ek. We can now define a so-called dot product for these vectors. In R2, if we have an orthonormal basis, we can write the dot product of two vectors as the sum of the products of our vector components. And now we can do something similar for functions. Here we take the product of the function values, and instead of a discrete sum, we write an integral, which is basically a continuous sum. In order to obtain a finite result, we only integrate over a characteristic interval, which in the case of a periodic function is one period. And in order to make the result not scale too much with the period, we divide by the period. You might also have noticed that there's a star symbol next to one of the functions. This is the complex conjugate symbol, and it becomes necessary in the complex case if we want the norm of a function to be a non-negative real number. The norm of a vector is simply defined as the square root of the dot product of the vector with itself. Let's now see how to compute the coefficient ck in our Fourier series, and understand why these complex exponential functions are really enough to build all well-behaved periodic functions. Let's start by looking at some important properties of these complex exponentials. The first property is that for the norm of each basis function, we obtain 1. If we take the dot product of two complex exponentials with different frequencies, we obtain the following result. Since k minus k prime is a non-zero integer, the exponential function completes an integer number of rotations over the interval from 0 to p, and its average value over a full period is 0. Together, we can express both of these properties in the following equation. Here, the so-called Kronecker delta, delta k prime, is 0 if k is unequal to k prime, and 1 if k is equal to k prime. With that, it should not be surprising that our basis functions are called orthonormal. This means that they are both orthogonal, meaning that the dot product of two different basis functions is 0, and they are normalized, meaning that the dot product of a basis function with itself, i.e. its norm squared, is 1. The orthonormality of our basis functions makes determining the coefficient ck in the Fourier series of our function very simple. Let us first multiply both sides of the equation by the complex conjugate of ek prime and integrate over one period. Since the ck do not depend on x, and the integral of a sum is the sum of the integrals of the individual terms, we can pull out the sum expression and write both sides as dot products. The dot product on the right reduces to our Kronecker delta. Thanks to the Kronecker delta in the sum, all terms vanish except the one where k equals k prime. This isolates the coefficient we're after, such that we can write the following. The coefficient ck in the Fourier series of our periodic function f is therefore the dot product of f and the kth basis function, which is exactly how obtaining the kth component of a vector works in basic vector algebra if we have an orthonormal basis. But how do we know that all the basis functions ek are really enough to build all the functions that we want to describe? Or in other words, do these functions form a complete basis of our vector space of p-periodic functions? We now know that if our collection of basis functions ek is complete, we should be able to write any well-behaved complex periodic function as this series. We now know that the coefficients ek can be expressed as the dot product of f and ek, which can be written as the following integral. Here, we integrate over x prime to not confuse the variable over which we integrate with our function variable x. We can now pull out the integral sign and include our function ek of x in the integral, since it doesn't depend on x prime. We can also pull f of x prime out of the sum, since it doesn't have any k dependence. Now we come to another interesting mathematical object. We've seen that in the world of discrete sums, the Kronecker delta can pick out individual terms. In the continuous world of integrals, the Dirac delta function plays a similar role. It picks out the value of a function at a single point. For a periodic function, it works like this. If we compare this expression with the expression above, we obtain the following identity. Since we started from the assumption that any well-behaved periodic function can be written as a linear combination of our basis functions, and we finally ended up here, we can say that if this identity holds, our basis functions are guaranteed to be complete, such that they span the entire vector space of well-behaved p-periodic functions. Now, we won't go into the full proof that this identity really holds for our complex exponential functions, nor will we discuss what well-behaved exactly means. There's also a lot more to say about the delta function. Technically, it's not a function in the usual sense, but a distribution, a generalization of the concept of a function. We haven't defined it rigorously here, but for our purposes you can think of it as the continuous analog of the Kronecker delta. Coming back to our goal of building periodic functions on the surface of a sphere, we can now more precisely state what we're looking for. We seek basis functions that exhibit simple oscillatory behavior in both the polar and azimuthal directions. In one dimension, we indexed our basis functions with a single integer k, but because the surface of a sphere involves two independent directions, we need two indices, L and M, to describe different oscillation modes. Our goal is now to express any well-behaved function defined on the sphere as a linear combination of the basis functions YLM. And we want to be able to compute the coefficient CLM with the dot product of the function f with the corresponding basis function YLM, where we integrate over all directions. We have seen that in order for all of this to work, our basis functions YLM have to form a complete orthonormal basis for the functions we are looking for. The additional sign in the denominator of the completeness relation is there to cancel the sign factor in the solid angle element d omega. Additionally, I have written down our periodicity requirement, as well as the requirement that our basis functions should be well-behaved, which basically means they should have no singularities or discontinuities. Our task is now to find explicit expressions for the basis functions YLM that satisfy these requirements. Now, just like in any non-trivial vector space, there isn't a unique orthonormal basis, and also here our basis functions are not uniquely determined by these requirements. The special set of basis functions that we are looking for in this video have an additional property that uniquely characterizes them, and which is connected to some of the applications that we discussed at the beginning of this video. Let's have a look at the Schrödinger equation for the hydrogen atom, as well as the Poisson equation for the electrostatic potential and the Newtonian gravitational potential. We don't really have to understand where these equations come from and what they mean, but we can identify something they all have in common. All of them involve the Laplace operator, which can be expressed as the divergence of the gradient. The gradient of a scalar field points in the direction of steepest increase, and the divergence tells you how much a vector field spreads out from a point. The Laplacian combines both. It basically measures how the value of a scalar field at a point compares to the average of its surroundings. If the Laplacian is positive, the point is lower than its neighbors, like a valley, and the field is increasing around it. If the Laplacian is negative, the point is higher than its neighbors, and the field is decreasing around it. In regions where the Laplacian is zero, the function values are basically equal to the average of the surrounding function values. If we set the Laplacian of a function equal to zero everywhere, we end up with the so-called Laplace equation. Functions that satisfy this equation are called harmonic. With appropriate boundary conditions, the graph of a harmonic function in 2D looks like an elastic membrane spanned by its boundary values, with no interior wrinkles, kinks, or bumps. Solving the Laplace equation will lead us to an exact expression for the basis functions we're looking for, as we will see in a minute. Since our basis functions involve the angular coordinates θ and phi, let us write the Laplace operator in spherical coordinates. We now want to solve this pretty complicated looking partial differential equation for the function g, and we're going to solve the equation by using the following ansatz. We assume that our function g can be written as the product of two functions. The first one depends only on the radial coordinate r, and the second one on the angles θ and phi. Plugging this back into our original equation, this leads us to the following equation. The derivative operators now only act on their corresponding functions, while the other function is left untouched. And since r is only a function of one variable, we can write its partial derivative as an ordinary derivative. If we now divide the equation by g equals r times y, we obtain the following expression. Let us now multiply both sides by r squared, and rearrange the terms such that on one side of the equation we only have radial dependencies, and on the other side we only have angular dependencies. Now, since both sides of the equation depend on different variables that can vary independently, the equation can only be satisfied if both sides are equal to a constant c. In these equations, the operator acting on our function r can be written as r squared times the radial part of the Laplace operator, while the operator acting on y can be written as the angular part of the Laplace operator. We therefore obtain the following equations for r and y. Since one can solve both equations independently, let us look at the second equation, which is basically an eigenvalue problem. When the angular part of the Laplace operator acts on y, the function simply gets scaled by a factor minus c. The functions y are therefore eigenfunctions of the angular part of the Laplace operator. I use the letter capital Y for a reason here. We will soon see that these functions satisfy our requirements stated earlier. In order to obtain an explicit expression for y, we can try to solve the equation by using a similar ansatz as before, namely assuming that our function y can be written as a product of two functions. The first one depends only on the polar angle θ, and the second one only on the azimuthal angle phi. Plugging this into our eigenvalue equation, dividing by our function y and rearranging the terms just as we did before, we obtain the following equation. Again, since both sides of the equation depend on different variables that can vary independently, the equation can only be satisfied if both sides are equal to a constant. Here we call the constant m squared, and the reason for this way of writing the constant is that it will give us a nice way of expressing solutions more conveniently in a minute. The equation for phi can be solved easily. The general solution is given by complex exponentials. Because of the periodicity of our phi coordinates, we must satisfy the corresponding periodicity requirement, which restricts our m's to only take integer values. The other equation looks very much like an ordinary differential equation that is well known in mathematics, namely the general Legendre equation, but for that we need to write the constant c as L times L plus 1. This equation can be solved with a power series ansatz, and the solutions are the so-called associated Legendre functions of the first and second kind. One can show that the solutions are finite, unique, and continuous only if L is an integer greater than or equal to 0, if the absolute value of M is less than or equal to L, and if we only consider associated Legendre functions of the first kind. Let's have a quick look at these associated Legendre functions of the first kind. The functions can be expressed using the following equation. If one does all the calculations, the first couple of associated Legendre functions look like this. Some of the functions are basically polynomials, while other functions also involve square roots of 1 minus x squared. With this, we found the complete solution to our eigenvalue problem from before, which is simply the product of the two families of solutions we just found, namely the associated Legendre functions with cosine theta as an argument, and the complex exponential function with different values of m in the exponent. Our general requirements also restricted the possible values that L and M can take. The solution that we have is now not normalized, meaning the dot product of the function with itself is not 1. However, one can calculate an appropriate normalization factor which makes the norm equal to 1, and which depends on both L and M. Our solution to the eigenvalue problem therefore looks like this. These functions are called spherical harmonics, and as foreshadowed earlier, one can show that they satisfy both the orthonormality and completeness relations from earlier, as well as the other requirements which we already enforced when deriving the solution. So this makes them ideal as building blocks for representing general functions defined on the surface of a sphere. As an example, we show the spherical harmonics for L equals 5 and non-negative m. In the visualizations, we're displaying both the real and imaginary part of these functions. Spherical harmonics and the associated Legendre functions they're built from are fascinating mathematical objects with interesting properties and many applications, but in this video we'll only stay focused on a few limited use cases. Now, after all these lengthy calculations, let's take a step back and remind ourselves of the big picture. Our goal was to describe functions defined on the surface of a sphere, in a way that mirrors how we represent periodic functions in one dimension, by expressing them as sums of simple oscillatory components. Each of these components, or basis functions, plays a role similar to a musical note, each with its own distinct shape and frequency. And just like in music, where harmonies are built from carefully tuned notes, we can recreate any well-behaved function on the sphere by combining these basis functions with the right amplitudes. If we choose these amplitudes, the CLM coefficients, just right, the result is a perfect reconstruction of our target function. To guarantee that this expansion always works and that the coefficients can be computed easily using simple dot products, our basis functions must satisfy the orthonormality and completeness relations. Additionally, our functions should be periodic in phi and should be well behaved. The spherical harmonics satisfy all these requirements, and they have another interesting property. They emerge naturally as the eigenfunctions of the angular part of the Laplace operator, which uniquely defines them and ties them directly to a wide range of physical problems, such as the Schrödinger equation for the hydrogen atom or the Poisson equation of Newtonian gravity or electrostatics. The indices L and M appeared as constants in our separation of variables ansatz that we applied twice. To ensure finite, unique, continuous, and periodic solutions, L and M are only allowed to take certain integer values. In quantum mechanics, the discreteness of L and M leads to the quantization of an electron's angular momentum, and similar constraints on the radial part of the wave function result in quantized energy levels. In order to get an intuition for how many spherical harmonics are needed to approximate a complicated function on the surface of a sphere, let's take a look at the decomposition of the Earth's gravitational field variations. On the right, we visualize how the approximation improves as we include all spherical harmonics up to a certain maximum value of L. One can see that for very large maximum values of L, there aren't that many changes visible. Higher values of L correspond to changes on smaller scales, so at the end only the fine details are carved out. The temperature distribution of the early universe, known as the cosmic microwave background, or CMB, has been measured with remarkable precision and can also be decomposed into spherical harmonics. The dominant contributions to the CMB are often subtracted or ignored in analyses. The largest term is the monopole component, corresponding to L equals 0, which reflects the average temperature of about 2.7 Kelvin across the entire sky. The next significant term is the dipole, L equals 1, which arises from our motion relative to the CMB. This motion causes a Doppler shift. Photons are slightly blue shifted in the direction of motion and red shifted in the opposite direction, introducing a directional temperature variation. To analyze the remaining structure, the true temperature fluctuations, we averaged the squared magnitudes of the coefficient CLM over all m for each L, and multiply the result by L times L plus 1 divided by 2 pi. This gives us the so-called power spectrum of the CMB. Different cosmological models, with different amounts of visible matter, and dark energy, predict different power spectra. Comparing these theoretical predictions to the observed spectrum therefore allows us to infer the composition of our universe and even determine its large-scale curvature. So far, we've seen how the spherical harmonics form a complete set of angular basis functions on the sphere, and how they emerge naturally from solving the angular part of Laplace's equation. But the story doesn't end here. Let's now take a step further and explore how these same mathematical tools help us to describe actual fields generated by real physical sources through something called the multipole expansion. In order to understand what kind of problems we can solve with this, let's go back to some of the equations I showed earlier, namely the Poisson equations of electrostatics and Newtonian gravity. Both of these equations look very similar because both electric and Newtonian gravitational fields can be described by very similar mathematics. The only differences are the prefactors and signs, which arise because different constants of nature are involved, and in electrostatics charges with the same sign repel, while in gravity masses always attract each other. Because of their similar structure, let us write both equations as the Laplace operator acting on our scalar field phi equals the density times a constant k that can be positive or negative, and we call this simply the Poisson equation. With our intuition for the Laplace operator from before, we can now say that this equation tells us that a positive density at a specific location creates more of a valley in our field phi, and a negative density, which is only possible in electrostatics, creates more of a peak at that location. In this visualization, a finite 2D density distribution is plotted in the xy plane, and on the z-axis, the solution to the Poisson equation is plotted. Solving the Poisson equation gives us the electric or gravitational potential at every point in space that is generated by this density distribution, and the corresponding vector field is simply the gradient of this potential function. Most of the time, we are interested in the field outside of the actual matter or charge distribution, so in locations where ρ equals 0. Then the Poisson equation reduces to the familiar Laplace equation. We have already figured out one part of the solution to this equation in spherical coordinates, namely the spherical harmonics, which describe the angular part of the solution. We now only have to solve the radial part to obtain the complete solution. You can easily verify that the two functions r to the power of L and r to the power of minus L plus 1 satisfy this equation, and because this is a linear differential equation, linear combinations of solutions are also solutions. Taking all possible linear combinations of our obtained solutions takes us to the general solution of the Laplace equation in spherical coordinates. In order to obtain a specific and unique solution to our problem at hand, we must impose certain boundary conditions that fix our arbitrary constants ALM and BLM. In the case of electric and gravitational fields, we want our field to go to 0 as we go to infinity. In order to achieve this, our constants ALM have to be 0, because otherwise we would have terms that grow with increasing radius as r to the power of L. Right now, we only have the solution outside of the actual matter distribution, but there's also a field inside the matter distribution that our exterior field should smoothly connect to. This is our second boundary condition that fixes our constants BLM. In the case where there is no density anywhere, the BLM are all zero and our gravitational field is zero everywhere. But if we have regions in space with a non-zero density, we have non-zero BLM, which we can obtain by computing the field inside the matter distribution and smoothly connecting our exterior field to it. This can only be done by solving the full Poisson equation, which we won't have time for in this video. I will simply write down the final solution for the BLM that arises when also considering the field inside the density distribution. Here, the factor k is the same factor we used in our general Poisson equation. So let us summarize the solution to the exterior field of a density distribution. It is given by the expression on the right, which involves spherical harmonics and constants ILM. These constants, which involve an integral of the spherical harmonics over the entire density distribution, are called the multipole moments. Each density distribution has its own set of multipole moments that describes it. The moment corresponding to L equals 0 is known as the monopole moment. In the case of gravity, this simply corresponds to the total mass of the density distribution, and for electrostatics, it corresponds to the total charge. The moments with L equals 1 are known as the dipole moments. In gravity, the dipole moment vanishes in the center of mass frame. In electrostatics, however, even in the absence of net charge, a dipole moment can remain. For example, when distributions of positive and negative charges are slightly displaced. The moments with L equals 2 are often referred to as the quadrupole moments, and then we have the hexadecapole moments for L equals 3 and so on. For perfectly spherically symmetric density distributions, only the monopole term is non-zero, and we obtain a spherically symmetric potential for our field. If our density distribution is almost spherical, but with small deviations, for example a slight flattening or other variations, larger values of L contribute less and less to the actual field. It is therefore often a sufficiently good approximation to only consider the first few terms in the solution, and to neglect the other ones. By doing this, non-spherical density distributions can become analytically tractable. In this example, we have a banana-shaped density distribution which is not in the center of mass frame. The green arrows represent the gradient of the actual solution in the region far away from the density distribution. For the red arrows, we only include terms up to a certain maximum value of L. For L equals 0, the monopole term, all arrows point to the center, assuming the total mass of the distribution is located there. If we now include more and more terms in the multipole expansion, we can see that including terms up to L equals 4 already gives us a result that is quite close to the actual solution. With this technique, one can also calculate how the rotational flattening of the Sun, or in other words its quadrupole moment, affects the trajectories of the planets orbiting around it, and similar things apply to the prediction of satellite orbits around our planet Earth. In turn, satellites around our planet can measure with extreme precision the variations in the gravitational acceleration they experience, and from that infer the various multipole moments. This is so precise that they can even measure the changes in the gravitational field caused by melting of ice sheets and changes in sea level. As we have seen, spherical harmonics are not just mathematical curiosities. They're powerful tools for understanding problems across physics, engineering, and beyond. What began as a question about wiggly patterns on a sphere turned into a deep mathematical structure with far-reaching implications, from modeling the shape of atomic orbitals to measuring the melting of ice sheets from space. It's a reminder that when we look closely at mathematical problems, we often find something more than just solutions. We find connections to all kinds of real phenomena. And sometimes those connections reveal deeper insights than we ever imagined.